What is IPv4? IPv4 addresses are 32 bits long, divided into 4 8-bit octets. So an example would be 192.168.1.1. IPv4 addresses are represented in decimal format divided into 4 8-bit octets, which are bytes. Each octet is separated by a dot, a format known as dotted decimal notation. So here's an IP address that you'll see, and this is dotted decimal notation. See? They range from 0.0.0.0 to 255.255.255.255, allowing for approximately 4.3 billion unique addresses. So you might think this is a lot of addresses, but it runs out. We are actually on a shortage of IPv4 addresses. Hence, we'll describe the need for private addressing soon. So there's classes of IPv4 addresses. Originally, they were divided into 5 classes: A, B, C, and D, and E, based on their leading bits. Class A, B, and C were used for general-purpose unicast addresses, while Class D and E were reserved for multicast and experimental purposes. So we're not going to cover E because it's not part of the CCNA, and I never saw it ever anywhere, and I don't think it's needed to know about experimental purposes. It's nowhere covered, and it's honestly unneeded. So we're going to cover A, B, C, and D. This is going to be helpful. So let's cover Class A. Class A has a range from 0.0.0.0 to 127.255.255.255. The leading bit is 0, and the default subnet mask is 255.0.0.0. This also goes by /8. Remember, basically, let me teach you something. /8s, any slashes of the prefix, every 8 is an octet. Remember octet? So 8 equals 255. So if you have 16, then you remember to 255, 255. If you have 24, 255, 255, 255. And if you have, like, say 22, 255, 255, but then another number like 192 probably here. So it's used for very large networks. Class B, its range is 128.0.0.0 to 191.255.255.255. Leading bits are 10, and the default subnet mask is 255.255.0.0. It's a /16, and it's used for medium networks. Class C, its range is 192.0.0.0 to 223.255.255.255. Leading bits are 110, and the default subnet mask is 255.255.255.0, and its prefix is /24. It's used for small networks. Class D, range is 224.0.0.0 to 239.255.255.255. Leading bits is 1110, and it's used for multicast. There's a Class E, but it's useless, and it will never be seen in this exam coverage. Special IPv4 addresses. Certain ranges of IPv4 addresses are reserved for specific purposes. Private IP addresses, also known as RFC 1918, is not routable on the public internet and used within private networks. This is for conservation of IP addresses for IPv4. Ranges go from 10.0.0.0 to 10.255.255.255 for Class A private addresses. And you need to note these down and memorize them because you will probably see them on the CCNA. For Class B, it's 172.16.0.0 to 172.31.255.255. For Class C, it's 192.168.0.0 to 192.168.255.255. That's Class C. Loopback address. So loopback addresses, also you need to know, range is 127.0.0.0 to 127.255.255.255, and it always starts with 127. Commonly used, 127.0.0.1. This is used for testing and diagnostics on the local machine. Here are other versions of IPv4 addresses that are reserved for specific purposes. There's the APIPA, or link local address, and this is usually given in a DHCP error, where your DHCP server cannot give you an IP address, so it gives you this. And it starts from 169.254.0.0 to 169.254.255.255. It's used for automatic private IP addressing when a device cannot obtain an IP from a DHCP server. A broadcast address is used to send packets to all those hosts on a network. So the example is 255.255.255.255, and it's limited broadcast address. CIDR, CIDR, is also known as classless interdomain routing, and it's knowing these 4 common prefixes and the subnet mask associated with them will make your life much easier when you're subnetting later. So I just told you about this, but /8 prefix, for example, it'd be this as notation, and 255. Remember, it's just 8, 16, 24, 32. So 255, 255, 255, and in this case 255. Number of addresses, 116,777,216, used for large networks. And we can just cover through these. Pause the video if you want to see, but this is just simple. And that is it. CIDR and subnetting. CIDR allows for more efficient IP address allocation by enabling subnetting and supernetting. Subnetting is dividing a larger network into smaller subnetworks. For example, splitting 192.168.1.0/24 into multiple /28 subnets. Supernetting is combining multiple smaller networks into a larger network. For example, aggregating 192.168.0.0/24 and 192.168.1.0/24 into the 192.168.0.0/23. Benefits of CIDR. It's efficient IP address allocation. CIDR helps in reducing the wastage of IP addresses by allowing allocation in more granular blocks. Improved routing. CIDR reduces the size of routing tables by allowing more route aggregation, which simplifies the routing process. And flexibility. It supports networks of various sizes, making it adaptable to different networking needs. So an example of it would be these, where suppose you have the IP address 192.168.1.0/24. The prefix length is 24, meaning that the first 24 bits are the network portion. The subnet mask is 255.255.255.0, and the network address is 192.168.1.0. The usable host address range from 192.168.1.1 to 192.168.1.254, excluding the network address and broadcast address, which is this. So if you further subnet this, then you could break it into smaller pieces, and you would get 192.168.1.0/26, which makes a subnet mask that, and it gives you 64 addresses, but then you can break it into more subnets. So each /26 subnet provides 64 addresses, so suitable for the smaller network segments within the larger 20/24 network. So basically, it enhances the flexibility and efficiency of IP address management and routing, allowing for better utilization of the finite IPv4 address space that exists. Subnetting. Subnetting is a process of dividing a larger IP network into smaller, more manageable subnetworks, or subnets. This is done by borrowing bits from the host portion of the IP address to create additional network addresses. The subnet mask determines the division between the network and host portions. For example, IP address 192.168.1.0 and the subnet mask being 255.255.255.0. This indicates that the first 24 bits are the network portion and the remaining 8 bits are for host addresses. So basically, this is my heavy recommendation. If I teach subnetting, I don't think I could teach it as well as this guy. This guy taught me subnetting. Go through his videos. They're insane. They're so good, and you'll learn everything you need to know about subnetting and all the secret strats for how to do it better and quicker. It's the best. So it's practical networking. Search this up. It's a huge video and millions of views. And basically, I'm making this course to help you. I don't need extra views just so I can waste your time teaching things that I don't think I'm comfortable teaching as well. So go on this. I really suggest this. This will teach you everything you need to know. And also watch the remaining 2 videos of his part where it talks about VLSM and FLSM, which are very useful. Anyways, configuring IP addresses. Configuring IP addresses is a fairly simple command. Basically, you'll start with the classic enable conft, and then you interface the interface, and you just write IP address and then write the IP address that you have. This will assign that IP address to G01, and that's all you need to know for configuring an IPv4 address. Private IP addressing. So, what is private IP addressing? Private IP addressing is essential for several reasons, particularly in the context of efficient use of IP address space, network security, and ease of network management. There are many reasons why it's super important. It conserves IP addresses. So the space is limited, and because there's only 4.3 billion unique addresses and there's a huge growth of the internet and many people own many devices, it's almost finished. So private IP addressing allows organizations to use a bunch of the IP addresses without consuming the public ones. This helps conserve the limited amount of IP addresses. And there's enhanced network security because they're not routable on the public internet, which makes it not being able to be accessed from outside the local network, which gives it a layer of security. And keeping the traffic isolated from the public internet Organizations can then protect their data better. And then there's NAT. Private IP addressing works hand in hand with network address translation, or NAT. NAT allows multiple devices on a local network to share a single public IP address for accessing the internet. When a device with a private IP address needs to communicate with the internet, NAT translates that private IP address to a public IP address. This not only conserves public IP addresses, but it also makes the internal IP structure from external networks, adding an extra layer of security. Internal network organization. Private IP addressing allows organizations to design and segment their internal networks more effectively. By using a private IP address, network administrators can create sub-networks for different departments, teams, or functions within an organization. This segmentation helps in managing network traffic, improving performance, and simplifying troubleshooting. And also has scalability and flexibility, where you can easily add more devices and use subnets using private IP addresses without needing to get more public IP addresses. This is super nice for changes in the company or anything like that, where you need growth or changes over time. So avoiding IP conflicts in mergers and acquisitions. When two organizations merge or one company acquires another, they often need to integrate their networks. If both organizations are using private IP addresses, they can avoid conflicts and overlap more easy. Like, they can avoid these overlaps more easily compared to using public IP addresses, because renumbering private IP addresses is simpler and manageable compared to renumbering public IP addresses. Cost efficiency. Using private IP addresses reduces the need for purchasing additional public IP addresses from internet service providers. This can result in significant cost savings, especially for large organizations with many devices. So, common private IP addresses ranges. These addresses were defined in RFC 1918, and there are 3 ranges of IP addresses that you need to know. And you need to know these. So, we covered this. 10.0.0.0. This is for that, for Class A. This is for Class B, 172.16.0.0, and this is for Class C. These are the 3 private IP address ranges, and you need to know and be able to identify these. IPv6 address configuration. It's as simple as IPv4 address. Basically, what you do is interface gigabit Ethernet 0.0, select interface. Then after that, you just plug in the IP address that you have but you write IPv6 address. Then you exit, and you have to configure this command, IPv6 unicast routing, so that it can be routed across the network. To verify, you can do show IPv6 interface on the interface that you configured it on. Let's cover the different types of IPv6 addresses that exist. IPv6 addresses are classified into several types based on their intended uses: unicast, anycast, multicast, and modified EUI64. Unicast IPv6 addresses identify a single network interface. There are 3 main types of IPv6 unicast addresses: global unicast address, or GUA. These addresses are globally unique and routable on the internet. So an example would be this. Unique local addresses, which is ULA. These addresses are used for local communication within a site or organization. It's not routable on the global internet, and a range would be like this, or So look for FC and FD for unique local. When link local, these addresses are used for communication within a single network segment, automatically configured on all IPv6 addresses. So the range would be FE80. So FE80, anything that starts with that, is most likely the link local for IPv6. Anycast addresses are assigned to multiple interfaces, typically belonging to different devices. Packets sent to an anycast address are routed to the nearest interface in terms of routing distance. There is no specific range, meaning any global unicast address can be configured as an anycast address. Multicast addresses identify a group of interfaces, typically belonging to different devices. Packets are sent to a multicast address are delivered to all interfaces identified by that address. They start with FF. Remember this, FF. And an example would be this, where it's FF02.1, and all nodes are sent on the local network segment. EUI64. The modified EUI64 format is used to automatically configure IPv6 addresses. It involves creating an interface identifier from the MAC address of the network interface. This process includes inserting FFFE in the middle of the MAC address and flipping the 7th bit. Example would be 00-1A-2B-3C-4D-5E, and the EUI64 address would be 021A, and it just integrates it and flips the 7th bit. It's simple, but it works. Configuring these EUI64 addresses, it's simple. And to configure it using a modified UI64 format, just use these type of commands where you plug in the IP address, but then after that you write UI64, and this will create that UI64. And to check it, do the same run or like show interface command. So IPv6 addresses, configuring and verifying IPv6 addressing involves enabling IPv6 on network interfaces, assigning appropriate addresses, and using commands to verify the configuration. Understanding the different types of IPv6 addresses, unicast, global, unique local, and link local, anycast, and multicast, along with the modified UI64 format, is essential for effective IPv6 networking management and the CCNA. So, let's get to practice questions. See what you learned. What address is fe80./10? Give you a second to think about it. Answer is C, link local. Remember, link local addresses are fe80.10. The FE is a link local starter, so if you remember that, you should be good. What class address is 11.11.11.11? Answer is class A. Class A is what fits 11.11.11.11, and if you have trouble with that, go back in the video. What prefix correlates with this 255.255.0.0 subnet mask? Answer is B, /16. /16 is what correlates with that answer. How many bits in an IPv4 address? Answer is A, 32. So there are 32 bits in an IPv4 address. What type of address is this? Answer is A, global unicast. So this is a global unicast, and if you don't understand this, go back in the video, because I would assure you that you'll see at least one question in the CCNA like this. Thanks for watching so much, and if you want to see anything else, tell me in the comments below. Please like, subscribe, hit that notification bell so you know when my next video is out. And if you want to help and support this channel and tell me that you love this channel so much, there's a place for a donation of appreciation for this free CCNA course, and it's my Patreon and